You know those gray metal boxes you see on utility poles? The ones just kind of hanging out in substations? Yeah, they don't look like much, but inside is a piece of tech so elegant, so important, that our entire modern world would just stop without it. So today, we're going to peek inside that gray box and uncover the simple, brilliant magic that powers pretty much everything.
It really all comes down to a huge problem. How in the world do you get all that electrical power from a plant that's miles and miles away all the way to your phone charger? Well, the answer is a device that performs a kind of electrical wizardry. And get this, it does it all with no moving parts.
And here it is. This diagram right here, this is going to be our map for this whole explainer. I know, it looks like just a couple of wire coils wrapped around an iron square, but trust me, this is the key. This little device is what makes our entire electrical grid possible, and we're going to break down exactly how it pulls it off, step by simple step.
So first question, how does the energy get from one side of this thing to the other? I mean, look at it. The two coils of wire aren't even touching each other. And that right there is where the real beauty of this invention is. It's all about an invisible connection, a fundamental force of nature.
The secret here isn't about gears or switches or anything mechanical, it's just pure physics. The whole operation hangs on one of the coolest concepts in all of electromagnetism, the ability to move energy right through empty space.
And this is the magic word for today, mutual induction. This is the whole principle. Just let that sink in for a second. A current flowing in one wire can actually create a current in a totally separate wire, just by being near it. No physical connection needed at all.
And this quote from the source material just nails it. It says, the two circuits are linked by a common magnetic field. That magnetic field, that's the invisible bridge. That's what carries the energy from the first coil over to the second one. Okay, so let's actually trace the journey of the energy. We're going to start where the power comes in, on that first half of the transformer. You can think of this as the spark that gets the whole chain reaction going.
All right, before we go any further, let's meet our two main players here. On the left, we've got the primary winding. That's our input, where the power comes in from the source. And on the right, we have the secondary winding. That's our output, which goes to whatever needs the power, what we call the load. Simple enough, right? So here's step one. An alternating current, or AC, flows into that primary coil. Now, because that current is constantly flipping its direction, that's what alternating means, it generates a magnetic field that is also constantly changing. It's growing, shrinking, and flipping back and forth. This pulsing magnetic field is then perfectly guided along that iron core.
And you can see that first step happening right here on our diagram. The electricity, that V1, comes in, it flows through that primary winding, and boom, its energy gets converted into that invisible magnetic field, what they call flux, which you can see as the dotted lines flowing right through the middle of the core. Okay, so our electrical energy is now a magnetic field. Now for the really cool part, making the leap across the gap. Let's move over to that second coil and see exactly how that energy gets caught. So that pulsing magnetic field we just made, it doesn't just stay put. It travels right through the iron core and passes directly through the second coil of wire, the secondary winding. It basically envelops it, soaking it in this constantly changing magnetic energy. And here is the payoff. Thanks to something called Faraday's law of electromagnetic induction, anytime a changing magnetic field passes through a coil of wire, it will create, or induce, a voltage in that wire. All of a sudden, an electrical pressure, what we call an EMF, or electromotive force, just appears in that second coil out of nowhere. And this new voltage has a very specific name. It's called a mutually induced EMF. And it makes sense, right? It's mutually induced because it was created by the influence of that first coil. One coil made a voltage appear in the other, all thanks to that magnetic field they share. And that new EMF, that new electrical pressure, is what pushes a brand new current, I2, out of the secondary winding and off to power the load. And just like that, the journey is complete. Electrical energy came in one side, it turned into magnetic energy, and then it turned back into electrical energy on the other side. So cool.
So we've totally seen the how, but let's just step back for a second and really appreciate the why. Why is this simple little trick of invisible energy transfer so important that it unlocks our entire electrical grid? So let's just recap the whole thing. A transformer takes in AC power, turns it into a changing magnetic field, and then uses that field to create new power in a totally separate circuit. This simple, elegant transfer is what lets us send electricity for hundreds of miles at super high voltage and then safely step it down to use in our homes. And the most genius part? It does all of this silently, efficiently, with absolutely zero moving parts to break or wear out. It's pretty much a perfect way to move energy.
And that really leaves us with a final thought. The transformer is a perfect, big-scale example of mutual induction. But this same principle, transferring energy through an invisible field, it's everywhere now. It's in our wireless phone chargers. It's in medical devices. So the real question is, what's next? What other impossible things can we do with this fundamental, almost magical law of physics?